Hello again, this is the Pencrest High School AP Physics 1 video series. This is video 9E, DC Circuit Analysis. Now DC stands for direct current. Again, electrostatics deals with static or unmoving charged objects. Circuits deal with charges that move through a closed loop. The charges are typically electrons, which are provided by a chemical reaction that takes place inside the battery. Batteries supply the circuit with voltage, which can be considered the electromotive force behind the motion of the electrons. Before we look at the mathematics, we're going to take a look at the symbols used for circuit components. The only ones we're going to be worried about will be batteries and resistors. They look like the following. This is a single battery symbol. Usually the longer of the two contacts is considered to be the positive one. We see also here what's called a cell. We have a number of batteries sort of stacked up. All that does is change the voltage. So these are what batteries look like. The resistors in the circuit usually look like this. Sometimes they'll look like this, but this is the more traditional way, sort of this zigzag looking thing. The resistors are typically, again, appliances or devices that use the electrical energy to do something useful. Okay. Now, circuit diagrams in our cases will contain a single battery. We could have more than one, but we won't deal with those. And a number of resistors in a particular type of arrangement. How the resistors are arranged determines how the current and the voltage are kind of used by each one. There are two major types of arrangements. They're called series and parallel resistors. Our goal is to take the complex arrangement of resistors and replace it with a single equivalent resistance that's called Req. Then we can determine the total current that's supplied to the circuit by the battery. This Req is more or less what the entire circuit feels like to the battery. Now, first, in a series circuit, the resistors are arranged end to end, and the current only has one possible path to follow. Series circuits are also called voltage dividers because the voltage is split up among the resistors. So here we have a series circuit. We've got our battery here that's supplying a voltage V sub t. And then we see that we have R1, R2, and R3. They are arranged end to end. And if you look at the current that comes out of the battery, it's only got one option. It's got to go through R1, it's got to go through R2, it's got to go through R3. There's only one possible path for the current to take. Now, in order to solve for the equivalent resistance of a series circuit, we just add them up. So our equivalent for series is R1 plus R2 plus R3. On your formula sheet, looks like this. It's in a red box, so you know what that means. It has R sub S, meaning series, equals sigma R sub I. And the sigma, of course, means sum, and R sub I just means that there are I resistors in the circuit, so however many there are. Now, what we find in a series circuit is that the total voltage that's supplied to the circuit by the battery is divided among the resistors such that V sub t is kind of used up as the current moves through the circuit. We would see that the voltage drop across 1, which is V1, plus the voltage drop across 2, plus the voltage drop across 3, would equal the battery voltage. So battery supplies 9 volts of potential difference to the circuit. V1 plus V2 plus V3 has to equal that 9 volts. This is called Kirchhoff's loop rule. There's a couple of Kirchhoff rules that we'll look at. We consider this circuit a loop. As we go around the closed loop, the voltage from the battery is said to be positive, and then the drops across each resistor are said to be negative. So it is said that the sum of the voltages in the loop sum to zero. That's Kirchhoff's loop rule. Now the current, of course, only has one path to take, and we see that the current is the same through each resistor in the circuit. So whatever current is coming out of the battery here, the same current has to come back into the battery at the other end. So the same current, what we call I sub t, the total current supplied to the circuit, comes out of the battery, goes through R1, goes through R2, goes through R3, and then back into the battery. So in short, a series circuit is called a voltage divider because the voltage divides but the current does not. Now we look at a parallel circuit. The resistors are arranged such that they present options for the current to take. So when the current comes out of the battery, it comes to this fork in the road here. That means that the current has two possible paths. So some of the current's going to go through R1, and some of the current's going to continue on to split up again and go through R2 and R3. Parallel circuits are called current dividers because the current divides. The current splits up among the resistors. Now in this circuit that we see here, R1, R2, and R3 are in parallel. The current takes multiple paths, and to find the equivalent resistance of the circuit, we need to use reciprocals. So 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. We could extend this to however many we have in the parallel circuit. On your formula sheet, it looks like this. 1 over Rp, or R parallel, is sigma, the sum of 1 over Ri. Again, I is the number of resistors in the parallel circuit. Now, importantly, we see that in a parallel arrangement, the voltage across each branch of the circuit is the same. So the voltage drop across 1 and across 2 and across 3 is equal to the total voltage in the circuit. Okay, so whatever voltage we have here, that same voltage drop goes across each of the resistors. So the voltage doesn't split up. The current, however, gets divided among the resistors according to the path of least resistance. The smallest resistor in a parallel arrangement gets the greatest current. We see that the current through each of the resistors, when added up, has to equal the total current. This is a consequence of the conservation of charge, which we saw in electrostatics. We would see that because of the way current has to divide, again, that current comes out of the battery, has to divide among 1, 2, and 3. It's all going to come back together down here and go back into the battery. Okay? Now, we see that this is also known as Kirchhoff's Junction Rule. It says that the current going into a junction or any fork or split in the circuit must be equal to the current that comes out of the junction. Okay? Now, again, parallel circuits are called current dividers because the current divides among the resistors and the voltage does not. We'll take a quick look at the junction rule again. There's a junction here in this piece of the circuit. There's a junction at point A here. The current going into the junction, I1, must be equal to the current coming out of the junction, which includes both I2 and I3. So we would see that I1 equals I2 plus I3 based on Kirchhoff's junction rule. Okay, that's it for series and parallel circuits. Next up is the problem-solving strategy for analyzing complex DC circuits. Until then, enjoy, and I'll see you again soon.